we're talking about finite wings, how to predict drag and lift. So we're going to continue on with that. So the deal here is that if the wing is finite, then there's tips to the wing, and the pressure wings, when it's generating lift, will produce flow from the bottom to the top. And it creates downwash. And it changes the angle of attack based on how much lift we're producing and how long and thin the wing is with the aspect ratio. So we learned how to predict the induced drag last time. We calculate that from the lift and the aspect ratio. Right, it's CL squared over pi DAR, and we can add that drag to the profile drag of the airfoil and get the total drag of the wing. So now we're going to talk about, well, how do you get CL? And the effect on CL is the higher the lift is, the more the downwash, and the more the effect on CL. So if you're down here at the x-intercept, where the lift is 0, then there is no change in the angle of attack, or the induced angle of attack. So that this is 0, so there's no change in the angle of attack. So if you draw the lift curve for an airfoil, two-dimensional wing, and compare it to the lift curve for a finite wing, they both intersect there. Because at 0 lift, there is no downwash, and so there is no effect on the finite wing compared to the infinite. But if you go up to an angle of attack where we're producing lift across here, you can see that the airfoil has more lift than the finite wing for the same, sorry, I should be doing the other direction. Compare it for the same angle of attack, infinite versus finite wing. You get more lift from the airfoil or the infinite wing than you do the finite wing because we're losing that flow around the wingtips and we're losing some lift. And the higher the angle of attack, the more the lift, the more you lose around the tips. And so the difference between the airfoil and the finite wing is this slope. So we're going to call this the slope of the lift curve A0 for the airfoil, and we're going to call it A for the finite wing. So make sure you write that down in your book or your notes. A0 is the lift curve slope. It's called that because this is the lift curve, and it's the slope of that lift curve. So this is for an airfoil. And then A is the same deal. For the finite wing. Now for an airfoil, we have the data in the back of the book. We have an angle of attack. Let's say we're at 4 degrees. We go up and we read the point off. But we could also use the equation of a line if we did the slope and the intercept, which we could get from the graph. And we talked about how you can do it either way. For the airfoil, it's just easier to go to the graph, read it off, right? So for the finite wing, we don't have a graph for every different efficiency, every different aspect ratio. And so we're going to use a formula for the infinite wing. the formula is valid for finite wings, or for, I'm sorry, for infinite wings or finite wings. But for the finite wing, we have to use the formula. Just like here, we get the induced drag from a formula, and then we add it to the drag for the infinite wing. We're going to use the formula for the lift. And it's not a big deal, it's just the equation of that line. So it says CL is A times alpha minus alpha L equals 0, which is that intercept. Then you can look at the equation and say, okay, I understand what that's doing, because A is rise over run, right? And this is the run. You start here where CL is 0, and you run out a certain distance at that slope, and that's what you get for the CL. Notice this only works in the linear region. But for a stall, because this is not a straight line once you start looking over, that line equation doesn't work anymore because it's not a line. So A is the slope of the finite wing. We can do the lift of the airfoil with the formula as well. They both have the same intercept, they just have a different slope. But again, typically we use the graph. And the only thing we need next is what's the formula for A. Because we have a plot for A0 with the infinite wing. And so you need this formula to calculate the slope A. Talk about the formulas, we need to talk about the units. So A is a slope, so it's a delta CL over a delta alpha. It's delta Y over delta X, right? So what are the units on CL? Hopefully you're thinking nothing, right? It's unitless. So there's no units. How about alpha? It's an angle. Yeah, so it could be in degrees. Our plots are in degrees, or it could be in radians. So there's a different formula for A for either radians or degrees. And all the units on this are 1 over degrees or 1 over radian. Makes sense because if you plug it in the formula here, 1 over degrees multiplied by degrees gives you CL. So the units work out. So there's the formula. If A0 is per radian, and then here's the formula per degree. And the only difference is the 57.3, and if you look at that, you go, oh, that's 180 divided by pi. That's the conversion from radians to degrees. So if you see the 57.3 in there, you need everything's in degrees per degree. If it's not there, it's in per radian. we see normal stuff, right? The denominator of the CD of pi e with the AR in it. So same deal here. What this says is for a finite wing, we go to the book and we look up the tables and we calculate the lift curve slope for the airfoil. Then we stick it in this formula, and then we calculate A, and then we use that to give us a lift. So we'll continue our example from last time where we had the flying wing. We knew what the weight of the airplane was and how fast it was flying. So we were able to calculate CL for that airplane. So we're going to know CL, and we want to know, well, what angle of attack is it flying at. Let's go back to that example. We looked at this last time. And in that, we were given the weight, the altitude, so we had the density, we did the area, we did the velocity. So we calculated a CL of 0.81. Oh, right up down, yeah, 0.8. So now we said, well, that's CL, and then we use CL to calculate CD, the induced. So we did that last time. Remember, the induced drag for this thing is a lot higher than the airfoil drag profile. So now I want to find out, well, what is the angle of attack? So I'm just going to use that formula I just erased. And remember, this was an NACA 4412. So the first thing we're going to have to do is calculate A0, and then stuff it in one of these formulas. Calculate A, stuff A in here, calculate alpha. So step one, get A0 from the table or the graph. Looking, I don't have that chart scanned in. I think I put that on the overhead. We will do this. How well can you see this on the screen? I don't kick it. Can you see it? The numbers? Somebody tell me.
Is that good enough that you can read points off of it? Okay, so that's what I want you to do. I want you to get me the slope of that line right there. And I'll see how if I can hold it still. Or if you have your book, you can look this up in the book. A better idea. That way it's not moving. Oh, that's not bad. Especially if you're looking on your PC at the zoom. So give me the slope of that line. And you'll want to use a fairly large range of alpha. You know, if you just do a little dinky section of the line, you're not going to get very accurate. So I want the rise over the run of that line. Move around where you can see that one really explosive. I want you to do this because you'll be doing this in homework and on a quiz. And for some reason, students try to do this, and sometimes, occasionally, some of them get confused as to what is the slope. So I want you to do it now so that you go, oh, that's all we're doing. You got what? 0.065? What? 1.065. That is right. You did it per degree, right? You did what? Yeah, sorry, try again. Yeah. You got 1?
Yeah. Or like 0.1 or 10.
Well, which is it? 0.1. Well, so you're calculating a delta CL, right? So here's how I did it. I said, I went from minus 4 degrees to 4 degrees. Pretty sure that's what I did. So that's my delta alpha. Is that what you did?
I went from 0.8 to 0.4. And CL, and then my degree from 0 to 4.
Yeah, that works. You should get something fairly close.
Yeah, like 0.1.
0.1, that's better than 1 or 10.
Yeah.
Yeah, so I went from minus 4 to 4 just because that's over a large region. And I got, so the reason I went to minus 4, can you tell why that's an easy point to pick? It's where CL is 0. So I used the intercept. And then I read at 4 degrees, that's a large range, but not out of the linear region. And I got a CL of 0.8. You could have gone from 0 to 4. You go much past 4 upwards, then you're starting to get into the non-linear region. So you had it right. It should be about 0.1. And what are the units?
1 over degrees.
Yeah, because we did degrees down here. So it's, often this will be quoted as per degree. So everybody comfortable with that? You're just doing the rise over delta y over delta x. But again, you got to pay attention to what are the units on the x-axis and and then make sure you read accurately and do a large enough range. If I had said, okay, I'm going to go from 0 to 2 degrees, that's just one little square, and it's going to be inaccurate because you can't read the delta CL very accurately, right? Okay, so let me move this back over here. Well, the next thing we need to do is now calculate A. That's A0. That's the airflow. So now we pull up that formula. So A is going to be A0. The units so we can track them. And then it's 1 plus. And then this is per degree, so we have to use the formula per degree, which includes the 57.3. Then we put in A0. We're going to put in pi. E, we have to remember what that was from last time. E was 0.95. Remember that was given to us. And then the aspect ratio was given because we knew the area and we knew the span of the chord. So the aspect ratio of that wing was 10, so this was given. This was given. Just the geometry of the wing and the lift distribution. All right, so punch this out in your calculator. With these formulas, you have to be a little careful because you make sure you start here. Because if you don't, then maybe you get it added to 1 and it's not divided properly. So I recommend when you're doing this on a quiz or on the homework, calculate that number in that ratio and then substitute it in. In other words, let's do that. Show that intermediate answer. So what are you guys getting for that? And the reason I want you to get into the habit of doing this is because when you get into 514, when you take that, this formula will be like 3 times bigger because it's more accurate. And it's got a whole bunch of sines and tangents and stuff in it, and it's hard to get lost. It's easy to get lost in it. What'd you get?
0.192.
0.192. Yeah. Anybody else got that number?
Yeah.
You got that? So that sounds right. 2 people vote for that number, right? And then punch out the whole thing. You should get 0.08385. And the units are per degree because the units up here were per degree. Really big clue, hint, sanity check is what it's called. If this number ever turns out to be bigger than that number, there's a problem. This number is never bigger than the number up here for 2 reasons. One, we know the lift curve slope of a finite wing is less than the lift curve slope of the infinite wing. So that would violate that. And also, look at this. We've got a number divided by 1 plus a positive number. So the denominator is always going to be bigger than 1, so this number is always less. So if you get a number like 0.13, you did the calculation and you put in 0.1, go back and check. There's a problem.
So always be greater than A.
A not always greater than A. So now back to the original question. What is the angle of attack? Well, CL is 0.8. Yeah, did I get that right? 0.8. We now know our lift curve slope. And alpha L equals 0 is minus 4 degrees. Another word of warning, it's really easy to forget both of those minus signs. In the same way that when we were doing the lift curve slope, we had 0.8 minus 0 over 4 minus 4. Right? It's really easy to mess that up. So the same deal here. Make sure you pay attention to that minus sign and that minus sign.
Why is that minus 4?
Why is which minus?
Why is the alpha L equals 0 minus 4 degrees?
Why is this a negative 4?
Yeah.
Because we go back to the plot. See if I can find it. That's the intercept. And the intercept is at, where does it cross the 0 axis? You go down, it's at minus 4. Yeah, it's just straight from the graph. And this is different than the angle of attack of the infinite wing, the airfoil. Remember, it was 4 feet. So if we want to build an airplane, we have to put a finite wing on it because we can't build an infinite wing. And then we want to be able to predict what angle of attack it will fly at. Before we started the finite wing stuff, we were talking about subsonic and supersonic flight. I thought I'd bring this up. There used to be an airliner called the Concorde that flew supersonically. It was a commercial airliner, and it flew from New York to London in 3.5 hours. Normally that flight takes about 7 or 8 hours. On October 24, 2003, the airline, the Concorde, flew its last flight. And passengers paid $6,000 to fly from London to New York. And then there were special dignitaries and guests that flew back so that they could say they were on the last flight of the Concorde. This thing flew at 1,350 miles an hour. Compare that to like a 777 or a 747 that cruises at about 530, 550 miles. So it crossed the Atlantic fast. Essentially, if you took this flight, you could leave New York early in the morning, jump on the flight, go to a meeting in London, jump on a late flight back, go to London for a meeting, and come back in the day. It would be a busy day. But it was expensive. It was about $9,000. We're talking back in 2003 for a round-trip flight. This was one of the coolest airplanes built for passenger aircraft, but only 16 eventually were built because it wasn't cost-effective. People flew on it, but it cost a lot of money to build it and make it, and it never made money. Air France and British Airways were the only airlines that buy this airplane. And the
was imminent after an airframe Concorde crashed in Paris in the year 2000, and it killed 115 people. The United States, prior to this, during this airplane development, was building something called the SST, the supersonic transport, to compete with this. And that airplane was banned. In other words, all supersonic flight over the U.S. was banned for a variety of reasons. So that SST program was banished because there was no market for a supersonic airplane flying over the U.S.
Commercial supersonic?
The what?
Is that commercial supersonic?
It was going to be a commercial supersonic airplane. Fighters, of course, can fly supersonic all the time. There are a lot of companies now working on supersonic biz jets because there's now new technology where they can suppress the sonic boom, and that was one of the biggest objections, is that if there were sonic booms happening all over the U.S., it would disturb people, it would disturb animals, it would disturb a lot of wildlife. If there were booms happening, I don't know how you feel, but at 3 a.m. every night a sonic boom in your house. You might object to that. But these boomless airplanes disperse the sonic boom in such a way they shape the fuselage and wings so that the sonic boom doesn't reach the ground. This is a cool looking airplane. Notice the wing. Definitely a delta wing, and we talked about the advantages of a delta wing staying inside the shock wave coming off the nose of the airplane. So this had a delta wing. Big, giant engines, because even when you're flying supersonically, even if you design it right, you need a lot of fuel, a lot of thrust to maintain supersonic flight. That's why it was expensive to operate. And there's the front view of it. Big engines, delta wing. Top view. It flew at about Mach 2.0. Pretty fast. Interestingly, when it's flying that fast, the temperatures of the nose and the skin get pretty hot. This is degrees C. This is 127 degrees C. You get approximately double that to get so the skin had to be designed to handle the higher temperatures as well. We're at 26,000 gallons of fuel, 17 miles per gallon per passenger, which is comparable to a big Ford pickup per passenger. The fatal accident happened to take off LaGuardia. I forgot whether it was LaGuardia or Charles Bell. But what happened was a tire blew out during takeoff, flew up and ruptured the fuel tank. So that's why the plane and it took the airplane out and crashed into a hotel or an apartment complex in Paris. So everybody on board was killed, as well as 4 people. Oh, some interesting design features on this airplane. The nose and the windscreen here change depending on the flight, how fast it's going. Notice the nose points straight out, and there's a windscreen here. That's what it looks like when it's a cruise in supersonic. Because of the delta wing, when it comes in for a landing, it's pitched up at a pretty high angle to attack. And so the pilots have a hard time seeing the ground to do a landing because the nose can stick straight up, so the nose can actually droop down. And that visor came retracted so that the pilot could see and take off and land. Like I said, supersonic flight is not dead. There was a big push 10 or 15 years ago. And it's still going on in the military is hypersonic flight, which means you're flying at Mach 6. You could fly a Mach 6, you could go to New York and Tokyo in 2 hours. That would be amazing. Scramjets, these are supersonic combustion scramjets. So the air comes into the jet. Most jet engines, the air slows down to subsonic, and then you burn the fuel, subsonic flow, and then you shoot that back. The scramjet never goes subsonic inside the engine. The fuel burns in supersonic flow. And a lot of the research was, well, how do you keep the flame from essentially being blown out by the fast air? So they have to design special flame holders and ways to combust the fuel. And I believe what they did eventually was that they would just, the air would come in and compress and heat up so much, they just spray fuel in it and it would combust. I think that this is my area of propulsion, and you'll hear more about this in propulsion. These are airplanes that look like this. This is starting to look like a UFO. It's essentially a flying body, a wing body. There's hardly any wing on it. It's a lifted body. The fuselage itself is the wing. It flies fast. Every once in a while you hear about something called a pulse jet. A secret military aircraft flying over the desert in California. Flying very fast and making a weird pulsing noise. That's a different kind of propulsion. It's scramjet. I think the military hasn't released any information about it, but people suspect it was a military aircraft. So there's even faster flight. I think we're looking at that. Maybe someday you'll get to fly on the supersonic business jet if you become rich and famous. Oh, by the way, there's a new homework posted. We'll go over it on Friday and quiz and due date is on Monday. Which ends chapter 5. So that puts us starting into chapter 6, which is aircraft performance. So next up, but first a heads up about next time. We'll get into this. I'm going to start this real quickly. But next time, I'm pretty sure on the syllabus, I'm going to stick to this. I saw it in the syllabus. I'm going to talk about X-plane. And it's beneficial if you bring a handout. Actually, I'm changing my mind. I'm going to print this out and give it to you. If you're on Zoom, I'm going to put this on Blackboard. It would be helpful to you to print it out at home if you're not going to be here. Because you're going to want to take notes on it and write down the menus. Just take some notes and menus that I go through. So I'm going to pull it up on the computer and demo that handout in class. So the handout on Blackboard. Even better, if you want to download the X-Plane demo, grab X-Plane 9.0, actually it's 9.73, and have it ready on the computer. If you're in here, all of the computers on this desk here have X-Plane installed. So grab that and you can follow along and do the menus as I do, or take notes and then you can go back and use it. So be ready for that next time. Pretty sure we'll get to that next time. If not, then it'll be in the class after that. Here's where you find X-Plane 9. the demo. And here's a download for free X-Plane electric demo. Don't do that unless you want to. But it takes a pretty decent graphics card. You scroll down, so you get to this page now, you scroll down. One installer for all X-Plane, don't do that. Older versions, see the older versions download page. So if you want to just write down the URL, it's xplane.com/desktop/try/older. It's easier just to remember xplane.com. Here you can get X-Plane 10. Here you can get X-Plane 9. So you're going to want to download the X-Plane 9 demo. Here's the Windows version. Here's the Mac version. Here's the Linux version. You can even download 8, but I use 9. It's pretty full featured. So you can have that available to use, and it's available on this app. All right, so you can have that available and ready to play with. And you can fly it. The demo version limits where you can fly it, what airplane you have available. But it's full featured, and the part of it that we will use to design our airplanes in called the Plane Maker is fully featured in the demo version. I've lost my ability to get back in this video. You might know it's better than I do. Here we go. All right, sorry about that. We have a few minutes. Let's talk about airplane performance. So this is an audience participation thing we're going to do right now. You guys on Zoom, we should be able to hear you over the overhead speakers. Somebody on Zoom say something.
Can you hear me clearly?
They're all asleep. Too shy.
I'm sorry, what was
Anybody
that?
here on Zoom? Are you on
Yes,
Zoom?
I am.
You're not?
I can hear you over here.
No, I'm talking about talking so that we should be able to hear people on the speakers overhead. If you're on Zoom. Okay. Unless I'm muted. Is anybody chatting? You're talking. Okay, now say something. Hello?
Can you hear me now?
Yeah, good deal. Okay, that works. I'm just having speakers right now. Okay, you're going to buy a car. What specifications do you look at when you're buying a car? Tell me what fuel. So, MPG, right?
How much gas does it take you to go 400 miles? Anybody else? Another one. Like, right, the number of people.
Safety standards.
Safety, so the crash rating. We definitely don't like to talk about crashes when it comes to airplanes, but it's important. Features. Somebody else what? Features. Features? What kind of features? Sorry, cruise control, so like radio, something like that. Stereo, radio, cruise.
How fast that AE takes off.
How fast what?
How fast it takes off.
Oh, so acceleration.
Yeah.
Transmission. Automatic or manual.
How much it can cost.
How it lifts.
So somebody said towing power.
So horsepower.
Maintenance.
You don't care about that because you spend the $3,000 get the extended warranty, right? Maintenance. Okay, something else. Anything?
Oh, it lifts.
Looks. How about top speed? Somebody said towing, right? So what was that? So that's really into the horsepower, right? How big's the engine?
How many miles are already on it?
So you're talking about a used car. I'm talking about a new car.
Oh.
That's important, yeah, used car, how old is it? What?
How many miles do you usually go? How long
Oh, like, so reliability.
yeah, like longevity.
Sellability.
What else?
Sellability. How much the price the appreciates.
Oh, yeah, how late it's on. So on airplanes, when we're talking about airplane, we're talking about performance. We're talking about a lot of this. We want to know, well, what's its range and endurance? How far can it go on tank of gas? What can it last? We want to know, with regard to acceleration and power, we want to know how fast it can climb. Because, I mean, it will accelerate down a runway, but that's not what you do most of. You want to know how fast it can climb, how much extra power does it have to get to altitude. How fast, what's its top speed, what kind of range can it get at the cruising speed, that's related to the drag. This is weird, we don't care about this for a car, but how slow can it land or take off? In other words, stall speed, right? With a car, how slow can a car go? Zero. Right, because it can stop. How quickly can it turn, pull up, or push over? Nobody said that about cornering, or the ability to corner, or related to that. How fast it can fly. So those are the things we look at and we'll talk about. Maximum load, how many people can carry, what cargo can carry. So we'll start the next time we'll do X-Plane, I'm pretty sure. Be ready for that because it will be Wednesday or Friday. All right, see you then.
Once we got to the slope back in Appendix D, I kind of got lost. Can you upload this lecture to Blackboard?
Yeah, I'll do that. I noticed I'm a couple lectures behind, so I'll be happy to do that.
All right, thank you.
I have to pull it into Camtasia, and then it takes about an hour to process the video. I just have to remember to come back to it after I do that.
All right, thank you.
Put up there sound.
Oh, how noisy is that? Yeah. The airplane does maybe even more important.